let's come back to our class. So basically, for the last hour, we have been talking about, the general idea of approximation algorithms. So in particular, in terms of approximation algorithm that in general, we probably want to deal with, for instance, some NP-complete problem. But in general, we cannot, for some NP-complete problems, at least for now, we cannot expect that we can satisfy all of the three features that solve the problem of optimality, solve the problem in polynomial time, and also solve an arbitrary instance of the problem. So these three are just, at least for now, people don't know how to satisfy all of them together. So our target here, in general, about like the strategy of approximation algorithm, is still that we can solve the problem in polynomial time and so an arbitrary instance of the problem. But maybe we probably cannot solve it to optimality, but instead we solve the problem. Here, this is the definition of the row approximation algorithm, is that we can solve the problem within a ratio a row of the true optimum. But a very important point is that we actually need to prove that a solution's value is close to the optimum, even without knowing what the optimum value is. So this is basically a proof that we already have shown in this Graham's theorem, that basically this greedy strategy of this scheduling algorithm is actually a true approximation algorithm for the load balancing problem. So here, basically for the last part of the lecture, in the last hour, we have been talking about, how we can actually further improve this. So in particular, the idea, that we got into is that maybe ideally we can, for instance, we can first sort the processing time of all the jobs here, and then we basically follow this rule of the longest processing time. So basically, we have this kind of idea that at the beginning, we just sort the jobs processing time in descending order, T1 larger than T2 until larger than Tn, and we just use this order into the list scheduling algorithm. And what we are going to prove here is that actually this LPT, this scheduling idea, is actually going to be a 3/2 approximation algorithm. Okay, so let's do the proof here. Okay, so basically we are going to follow a similar strategy that we use in the two approximation proof due to Graham. So in particular, we are basically going to follow the same similar pattern, but maybe you can imagine that we want to use something, for instance, like the lemma 3 here. So there is actually a factor 2 here, and this is a specific place that we are going to make the improvement upon the original two approximation algorithm. So in particular, we say that similar to the above proof. So what we can do is that basically we are still going to consider this so-called bottleneck machine. So in particular, consider the load Li to be, I think I should use the of the bottleneck machine. The machine that reaches the max span. Okay, so similar to the notation in the above proof, so let job J be the last job. So let's take a close look about the ith machine here. So we talk about the case. So for instance, if the job K is the only job on machine I. So we know actually in this case, the current scheduling. So recall that actually the machine I is the bottleneck machine. And if it is the case that the bottleneck machine only contains one job, so in this case, we know that actually the current scheduling is optimal. So why is this the case? So actually by the lemma, I think it is actually going to be the lemma 1 here. So by the lemma 1 here, basically this lemma 1 is L star is going to be larger than, the max of all the TJ, basically larger than or equal to the job that taking the longest processing time. So basically why actually this is optimal? It's just like actually by lemma 1. we of course are going to know that actually L star is going to be larger than basically TK here. I mean, it is larger than the maximum among all the processing times here. So of course, I mean, the job K here is one of the jobs. So we definitely going to know that L star is actually larger than or equal to TK here. But on the other hand, we know that actually the job J here is the last job. But basically, we have assumed that actually Li is the bottleneck, and job K is the only job. This is actually implied that L star is smaller than TK. It must have the case L star equals to T. And basically it says that for the case where if the bottleneck machine, if you only have one job, which is job K here, then this is just going to be, a very easy task that we have been talking about, which is actually you have already given the optimal solution. Okay, so therefore, we can say that actually we can assume that actually a machine I has at least another job before Q. Okay, so in this case, it is basically the part we are going to use the greedy strategy. So in particular, in this greedy algorithm, basically in the above, in this figure here, we have established that actually Li minus Tk is smaller than 1 over m times the summation of basically this part, times the summation of all the processing times. So here, we are going to use the same inequality here. So we say that we are going to still have that actually Li minus Tk is actually a smaller than 1 over m with the summation of let's write this first, write this down, and actually this equals to the summation 1 over m times the summation of a from 1 to n j, and actually this is smaller than L star, and this is recall this is actually going to work by lemma 2. So this is actually still going to work. And furthermore, we are going to use the lemma 3 here. So by using lemma 3 here is basically the place that we are going to have a better understanding about what is TK here. So in particular, when we assign TK, I probably should say a job K, that's this reads better in English. So in this case, we know that actually it is assigned to machine I with already a job there. So this is actually going to imply that K is at least m plus 1. So otherwise, for the first m jobs, it is always going to be assigned to an empty machine at that time. So this is a very important point, and recall this is actually showing that K is at least m plus 1. So in all, we are going to have that Li equals to Li minus Tk plus Tk. So in the above, we have shown that Li minus Tk is actually smaller than L star. And basically here we know that actually Tk here, so because T is actually at least m plus 1 here, and we know that all the time is actually assigned in a descending order. So we know that actually Tk is smaller than or equal to Tm plus 1. But according to the lemma 3 here, so lemma 3 here, we know that L star is at least 2 times Tm plus 1 here. So this is just going to be smaller than L star plus half times L star equals to 3 over 2. So this specific point is due to lemma 3. And this finish our proof that basically this LPT, this scheduling algorithm, is going to give a 3/2 approximation. So a remark that we are actually going to give here. I mean, maybe you want to ask, I mean, this is, I mean, in this proof, I mean, this proof that achieves that 3/2 approximation, if you only look at like one job before K here, basically we have this lemma 3 here. So in particular, I mean, we can actually further improve analysis. I mean, by looking more jobs and using like pigeonhole principle at like a larger size and like have like a more sophisticated analysis about the behavior of the greedy algorithm. So in this class, we are actually satisfied with this 3/2 approximation. So in particular, it is possible that to give using a more sophisticated analysis. We can actually even further improve the approximation ratio bound here. So in particular, we can improve that LPT is actually a 4/3 approximation algorithm. And this is actually a tight analysis for LPT. I mean, this is probably just going to be a little bit more sophisticated, bring into like more structure of the greedy algorithm. And this is the part that we are not going to introduce. So basically for the lecture today, I guess I just want to show you the intuition that basically, I mean, for designing a good approximation algorithm. So typically, I mean, a good greedy strategy is going to work good enough. And looking into this greedy strategy, and actually we use the greedy property that at the first we can give a 2 approximation algorithm, and then further looking at, I mean, in general, what is a good way to assign like the processing times of all the jobs here, and actually according to like if we sort the, I mean, in descending order, and we first process the job taking the longest time, and then until we process the job taking shorter times. Basically, we are going to give this LPT the scheduling algorithm that gives. I mean, we can give a clear analysis that has like a 3/2 approximation, but in general, it can be a 4/3 approximation. And basically, this give a good approximation algorithm in general for the load balancing problem. Okay, so this is pretty much what I want to talk about for the load balancing problem. So is there any question for this proof that this 3/2 approximation proof and overall about the load balancing problem? Okay, so if there is no question, I think we can move on to the next topic. So today, when we talk about approximation algorithm, we will talk about 2 new problems. I mean, this load balancing problem is the first new problem. And the second problem that we are going to talk about is called a center selection problem. And the third problem that we are going to talk about is an old problem, the knapsack problem that we talked about when we talk about dynamic programming. So we are going to talk again about the knapsack problem, about in particular how we can give a good approximation algorithm for that. But before that, let's talk about the second topic, the center selection problem. So this is actually a very important problem in big data. In general, I think in data science. So the problem is stated as follows. The input of the problem is a set of n sites. So we say there are actually some S1, S2 until Sn. So also basically we are talking about a distance metric. I mean, when we talk about like a distance metric, actually, it is very important that actually satisfies the triangle inequality. Actually, the distance between 2 points x and y is actually smaller than the distance between x and z plus the distance in z. So this is called a triangle inequality. And also, I mean, the distance to the point itself is going to be 0. And also this is unoriented, and actually the distance between x and y equals the distance between y and x. So we know that we are actually talking about some n sides here, and we know the distance measure that we are talking about. So furthermore, for any set C here, so we are actually going to define the distance S and C to be the minimum, because the C here is a set here. So here we are actually talking about the minimum between all the small c in this set C here of the distance Si and C. So in particular, as long as we have a certain set, we have like a certain set Si, we have another set C here. So we want to talk about this corresponding distance. This distance is just like we want to take the distance from Si to the closest element. So as long as we have a set, we can have such kind of a definition. So having the distance, between like a specific set and like a corresponding set C here. So in particular, after having this definition, we can define another function called R of C here to be the maximum among all the sites. To this C here. So intuitively, you can just imagine this is also called the smallest covering radius. Then you just consider all the points in this set C here and like draw a sphere with radius RC here. So this RC is just the radius that you can actually cover all of the sides on SI here. So it is actually smaller than that. Since there is actually, you are taking the maximum. So maybe, so definitely one of them is going to reach the value. So if the radius that you're choosing here is smaller than this RC, some of the sides SI you are not going to cover. But actually, if you, as I just mentioned, if you consider all the points in this set C here and draw a sphere with radius RC here, you're definitely going to cover all of the sides SI. So this is called the covering radius here, and the other discussion here, we just denote this to be RC here. So the goal of this part, which is the main problem for center selection, is that we want to find a set of centers C such that minimizes R of C. Of course, in general, we just talk about, okay, we want to minimize R of C. So for this problem, if we don't have any restriction, I guess this problem is just trivial. We just choose the set C here to be the set S1, S2, but that's it here. Okay, you just cover all the sides. But this is just going to be too trivial in terms of big data, in general, in data science. The main point is that we can regard this set C here as some kind of center set. We probably want to use like a small set C here to represent all the sides here. So in particular, hopefully, we have like a size requirement. So we say that subtraction that we apply here is that we say that the cardinality of C here is at most K here. So always because we are talking about the minimum here. So a key observation is that putting more, or if you have like a current set C here and you put like more vertices into this set C here, it is never going to make this R of C. Never going to make this R of C actually larger. Adding more vertices actually always going to help. So, in general, for the subtraction here, you're talking about like this cardinality of set C is smaller than or equal to K, but for our better presentation, we just say that the cardinality of C here equals to K. Okay, so is there any question about the definition of the center selection? So let's, for instance, see an example for the center selection problem. So a very common example is that maybe you can just imagine that each side is actually a point in the Euclidean plane. And actually a center can be any point in the plane. And the distance, I think we use the distance. It's just the Euclidean distance. Okay, so in terms of that, maybe you can just imagine, for instance, assume that we have this as our size and this as here. So if k equals to 3, so basically the center size C here that you're going to choose is probably going to look like something like this. I mean, basically, this is a good way that you can actually cover all the vertices. And also, on the other hand, you are going to take the smallest common radius. So I can tell you that actually this center size selection problem is actually also NP-complete problem. So this is in general very difficult to solve. But maybe we can actually also think about, I mean, some other strategies that hopefully, maybe we can actually give like a good approximation algorithm and follow the pattern that we have been discussing about. So from the case of the load balancing problem, I mean, we can in general think about, okay, hopefully some greedy strategy is not that bad, and hopefully some greedy strategy is going to give you a good approximation algorithm. So still, I mean, in general, as we have been talking about in the lectures for the greedy algorithms, the most important question is that what is the point that we are going to make it to be greedy here? So there are definitely going to be a different strategies. So let's first, for instance, see like a first attempt. Maybe like a first attempt. Is that, for instance, I mean, very naturally, we just want to, I mean, shrink the value of the smallest covered radius. We just want to decrease the value of RC here. So maybe we can do something like this. So maybe, for instance, we can put the first center at the best possible location. And we just keep adding centers. To best reduce the covering radius. I think this is probably something natural that, I mean, hopefully at the beginning you pick a good center. I mean, you at the beginning you just pick it to be at the best possible location. Then we just keep adding centers to best reduce the covering radius. So we can think about whether this is actually a good strategy or not. So in particular, maybe let's talk about, for instance, like such kind of case. So we have like a bunch of vertices here and a bunch of vertices here. So here we only have, like, roughly speaking, 2 clusters. And we have the case where, for instance, equals to 2. So what is going to happen for this case if we just run this greedy algorithm? So the first line says that we are actually going to put the first center at the best possible location. So if k equals to 1, the best possible location is probably going to be somewhere in the middle. So because this is indeed the place where actually you can cover all of the vertices with the smallest common radius. For instance, you have like here, then basically you're going to cover like this. This is really like a large radius compared to here. Maybe you're going to use like a relatively small circle here to cover all the vertices here. So if k equals to 2 and you use this greedy strategy, unfortunately, the first point that you are going to pick is actually the point in the center. I mean, here, probably quite far from both of the vertices. But actually, for the case where k equals to 1, this is the optimal way that you can do this. But after having picking this vertex for k equals to 1, and assume that actually originally you assume that k equals to 2 here. The first point is like this, and maybe for instance the second point is in the right hand side. But basically in general for the left hand side it's then quite bad. Or in general, maybe you want to think about this kind of greedy algorithm. You can probably clearly see that this is not going to give you a good a greedy-based algorithm because at the beginning, maybe your center is probably just like in the middle, but not so helpful for actually solving this kind of center selection problem. I mean, ultimately. And after having that, you maybe like the first center you choose here is actually wasting the way that you choose the center. So maybe for instance, especially in this case, k equals to 2 here, you can just imagine that this greedy algorithm is just going to be arbitrarily bad as long as, I mean, these two clusters are very far from each other. Actually, for this case, where actually R of C can be quite small, but I mean, the greedy algorithm makes it to be quite large. So this is probably not going to be a good greedy algorithm. Maybe you want to think about some other strategies. I mean, still, as we have been talking about, I mean, in terms of algorithm, I mean, for a lot of problems, I mean, greedy algorithms, they can give you good solutions, but you definitely need to have like a good way of making it to be greedy. So here, I mean, basically this first attempt is just not a good way to give us a good greedy algorithm. But actually what works? We can think about some other kind of greedy strategy here. So what actually works here is another greedy idea. So what kind of greedy idea it is? So basically we can say something like this. So we just repeatedly choose the next center. Will be the site. So in this greedy algorithm, all the centers that we choose are going to be a site, an input set here. So we are going to choose the next center to be the set of fourths from any existing center. And this is actually going to be our greedy strategy here. So, or formally, we can write down a pseudocode for this algorithm. So center selection, we are going to have this k and n as inputs, and also we are going to have s1 and sn. So at the beginning, the center set we select is going to be an empty set, and we repeat the following part for k times. So we are going to select a site Si with maximum distance SIC here. And then we just add Si to C. And after having run the algorithm and repeated for k times, we just return C. Okay, so this is basically our center selection algorithm. So let's prove something. I mean, basically we need to use the greedy point to prove that actually we are giving a good algorithm here. So the first observation that we make is that actually upon the termination of our algorithm, all centers in C, they actually are pairwise at least RC apart. Or in other words, all the centers we select, they actually have a distance at least RC between each possible choices of the centers here. So actually all the centers that we actually choose here, they're actually far from each other intuitively. Okay, so let's do the proof here. So the proof that we are going to give is something like this. So we are going to prove by contradiction. So assume the contrary. That let's say the distance between the centers CI and CJ is smaller than RC, where actually CI or respectively CJ is added in the F respectively. Let me check in the F respectively J iteration. And for our convenience, we just say that I is actually strictly smaller than J. So as we just mentioned, that actually a very important property of R here is that actually adding centers will only make R smaller or equal. This is because, I mean, for we can just do this using the following argument. So assume that we have like a C1, which is a subset of C2 here. We know that actually the distance between S and C1, I mean, just according to the definition, it's going to be the minimum of all the C in C1 of the distance S and C. But this is going to be smaller than the minimum of all the C in C2 of the distance S and C. Because giving more choices can only make a minimum of these values smaller or equal. And this is just going to be the distance of S and C2. So I think this is relatively straightforward. That actually, I mean, in general, a good property of this common radius, this R here is actually adding centers will only make this R smaller or equal. So this is a very important observation that we are going to make. And actually, this is extremely helpful that we can establish this observation that actually all the centers are actually pairwise at least RC apart. So why is this the case? So on the other hand, we actually know that actually when our algorithm runs the fifth iteration, I mean, we just imagine, I mean, it is our choice to pick the C and CJ into this algorithm. And basically, we are using a greedy algorithm. So as we choose C and CJ into our set in the ith and jth iterations respectively. So we basically know that actually they are going to have some good properties. So in particular, we claim CJ because is the farthest two existing centers. So together with the distance between C and CJ smaller than RC, this suggests that R is already smaller than RC. I mean, because when you choose the size CJ here, I mean, you choose this. And actually, when you choose this, you notice that actually the distance between C and CJ is already smaller than RC. So this is probably just this is just saying that actually the best choice that you are making here is that you're always going to choose, I mean, the current radius here in this current case is always going to be smaller than RC here. But this actually contradicting with our assumption. That actually it only that, excuse me, I think I should use this. The fact R only goes smaller or equal through iterations. But finally, it ends at RC. No contradiction. So this is just saying that all centers in C, they must be pairwise at least RC apart. Is there any question about the proof of this observation? Okay, so this is an important observation that we are going to use in our proof, and also is a proof strategy. So now we are going to prove that actually this greedy algorithm that we gave here is actually a two approximation algorithm. So in particular, let's see star be an optimal set of centers. So then we are going to prove that actually RC is actually smaller than 2 times R C star, where C is the output by our greedy algorithm. And we are going to prove this. So somehow, I mean, basically for this two, I mean, intuitively, this comes from, I mean, a triangle inequality here. But we need to figure out how actually this works. So in particular, we say that, I mean, following this observation here. So for this observation, it's just an observation. We say that actually the distance, I mean, basically the pairwise distance between all the centers in C that is actually what we selected for the greedy algorithm should be at least RC apart. So basically, I mean, the strategy is that we just prove by contradiction. I mean, okay, if two of them they're actually close, I mean, actually the distance is smaller than RC here. This is just going to violate the way that we we choose the size in this greedy algorithm. So basically, this is still, I mean, like in general, good strategy that we are going to use. And in particular, I mean, for this proof that actually our algorithm is a two approximation algorithm. We are also going to prove by a contradiction argument. So in particular, let's suppose, let's say that actually RC, I mean, the output is not so good. Actually, assume that RC is larger than 2 times R C star here. And let's see what it is the contradiction that we are going to encounter. So we can assume that, I mean, in general, I mean, we know that there is ultimately going to be an optimal solution. This is just the C star that we are talking about. So for our convenience, let's make more notation for the C star here. So for our convenience, we denote this the sets is C star as star equals to, let's say they are actually C1 star or C2 star until a CK star. Because we know that the cardinality of C and C star, they are both K. So for each I mean, we are going to, I mean, because we are talking about covariant radius, and we know that there is optimal solution. So we have like a further definition is that for each I in K here, we are going to denote BI as the ball of radius R C star centered. So we are basically going to draw a ball at a center at CI star with the corresponding radius just to do this on RC star. So we are going to make some arguments about like the relationship between C, the output of the greedy algorithm, and all, excuse me, and all the balls here that we are talking about. So the first claim is that actually not for any C in C here, C must be in one of the balls. One until BK here. So why is this the case? So otherwise, assume that, for instance, if maybe this C and C is not in B1, B2 until BK, this just implies, I mean, because the radius of all the balls here on the B1, B2 until BK here, we know their radius is actually RC star here, and the the vertex, the set C here you are talking about is not in all of them. So this is actually just going to imply that the distance between C and Ci star is actually at least RC star. I mean, this C is a capital C here. Is actually, I mean, I shouldn't say at least, it's actually strictly larger because it is actually not inside this ball here. Okay, so but on the other hand, actually, however, when we run our algorithm, so basically, an important thing that is actually assumed in this greedy algorithm is actually all C, they are actually sites from the inputs. And in particular, this C actually has distance. I mean, to the closest center in C star. I mean, larger than RC star. And this contradicting with the definition of RC star. Okay, so this is the reason for the first point that actually for any small c in the capital set C here, basically the output of our greedy algorithm, C must be in one of the balls, B1 until Bk here. So this is the argument on the one hand. So on the other hand, the relationship is actually also hold in a reverse kind of sense. So why I'm saying that this is basically saying something like this. So on the other hand, each ball B1 until Bk, they can only contain one of small c's. So why is this the case? So otherwise, suppose, let's say that Ci1, Ci2, they are probably both in Bj. Where Ci1 or Ci2, they're actually both in C. And of course, I mean, we are using different I1, I2 here, so we assume that they're actually not equal to each other. So what is the issue here? The issue is that since Ci1, Ci2, they are both in Bj here, we know that actually the distance between Ci1 and Ci2, they're actually, I mean, we just talk about, I mean, two vertices. I mean, this is Cij star, because it is the center of Bj is going to be Cij star here. So we are talking about, I mean, we have like a Ci1 and Ci2 here. I mean, we have two vertices in the same ball here. We are going to know that the distance between Ci1 and Ci2 is actually going to be smaller than the diameter of Bj. And the diameter of Bj here is going to be 2 times R C star here. By our assumption, we know that this is smaller than RC. Okay, so this actually established that the distance between Ci1 and Ci2 is smaller than RC. But actually by our observation, this is a direct contradiction. We know because we know that the distance between Ci1 and Ci2, they're actually larger than or equal to RC. Contradiction. Okay, so this is the conclusion on the other hand. So basically, I mean, these 2 points, I mean, is actually giving us a very good structure about the relationship between C and C star on these 2 sets here. So basically, we know that actually the 2 observations is actually about is going to imply that each ball I must exactly contain one of C in C here. Because we know that for any elements C in the set capital C here, it is going to be in one of the ball here, but each ball can only contain at most one of them. So it must be the case that actually each ball BI must exactly contain one of the C in C here. So for convenience, I mean, this is really good and really convenient in terms of notation here. So for convenience, we just denote the small ci to be in the ball BI here. And actually, we denote the set C here to be correspondingly to this small C1, C2, and CK here. So this basically, I mean, very good. I guess basically this gives a very good structural information about the relationship between C and C star here. And then we can basically finish our proof. So now we just take, I mean, any set S here. So basically, we want to have a good understanding about, I mean, what is, I mean, using the greedy strategy. I mean, based on our basically our greedy algorithm of choosing our way to choose the set C here. What is the good thing that we are going to satisfy here? So now we just take any set C, any set S from the original input here. So we just denote it's the closest center. Let's see, star as CI star. So we know that actually we have actually the distance between the set capital C here. I mean, we just do this by using a triangle inequality here. So we know that this is, of course, due to the definition of the distance, this is going to be smaller than S and CI here. And actually, due to the triangle inequality, this is smaller, going to be smaller than the distance between S and CI star, plus the distance between CI star and CI. And we say that this is actually true due to the triangle inequality. And after knowing this, we know that actually the first term is actually going to be smaller than RC star. This is just according to the definition of RC star. And for the second term, this is actually also going to be smaller than or equal to RC star because we basically based on our discussion above that actually this CI is actually in BI. And this just equals to 2 times RC star. And by our contradiction argument, this is actually strictly smaller than RC here. But actually here we are picking an any set S here, and then we know that actually the distance between S and C here is strictly smaller than RC. So this is actually going to give us a contradiction. So since S is arbitrarily chosen, this is actually suggests that actually R of C, this is a capital C here. So R and C equals to the maximum of odd I with the distance. As I C. This is strictly smaller than R, and this is a contradiction. Okay, so this just concludes that therefore our assumption is wrong, and we must have that R of C is actually smaller than 2R to start. And it finishes. Okay, I think I only have 1 minute, so let's actually finish the part for center selection, and then let's take a break. And if you have any questions, just feel free to ask during the break or at the beginning of the last hour. So a remark that we actually know for the center selection problem is that actually our greedy algorithm always places center sets, but is it is still within a factor of 2 of the best solution. And that is actually a lot to peak centers anywhere. And in addition, it is also known that although our algorithm, I mean the greedy algorithm, the strategy is quite simple. And here we actually have a two approximation algorithm. So for this center selection problem, it is known that unless p equals to np, actually our algorithm is already the best. And actually, unless p equals to np, there is no row approximation algorithm. For the center selection problem. For any constant. For any constant row strictly smaller than 2. So let's say 1.999. We are not going to have like a 1.99 approximation algorithm for the center selection problem in polynomial time unless p equals to. Okay, so this is pretty much about the center selection problem, and let's take a break until 10:05. And if you have any questions, just feel free to ask anything after. Okay, see you in 10 minutes.